Welcome back. This is section 4.7, problem number 6. We're working with Newton's method of finding zeros. And if you haven't seen my video about deriving Newton's method and what Newton's method is doing, I highly recommend watching it because it really helps me to visualize what we're even doing here. But for this video, I won't bother to explain how Newton's method works. We'll just start with the pre-derived form. And the question is giving us two graphs. One of them I'm calling it y1 is tangent of x, and another one I'm calling y2 is 7x. And we're looking for the intersection of these two. So that's what this upside down in-looking thing represents. It's an intersection. Where do both of them hit the same value? And it says where we're looking for is a non-zero value in the interval 0 to pi half. So we're not including 0 because if you'll notice, y equals 7x and y equals tan x do intersect at 0, but we're not interested in that one. We know that 7x has quite a slope, right? It's a rise over run of 7 to 1. And tangent, we know about tangent is that it starts at 0, and then as it approaches pi halves, it goes asymptotic. In this what would you call it? In this region, anyhow, tangent, of course, is an infinite function, as is 7x, but we're only curious between x equals 0 and x equals pi halves. It's called a quadrant in this quadrant, that's right. So, pi halves is approximately, let's take a look, pi divided 2 is approximately 1.57. So we'll use that because we've noticed that our intersection seems to be a little bit closer to pi halves than it is to 0. And that's why I decided to choose my initial value, which we'll call x1. I'm going to choose x1 as 1.5. And now the next step is, well, we know how to use Newton's method to find zeros on a single function, but how do we use it to find an intersection? And so with an intersection, what we're curious about is, when does y1 equal y2? And so we'll fill in this for y1 is equivalent to tan x, y2 is equivalent to 7x. And so we've now made a new function, right? What we can do now is we can subtract one of them over. So let's go ahead and write this is equivalent to 7x minus tan x equals 0, right? Because we subtracted tan x over, and really what we've really done here is we've solved for a new function of x. We could call it f of x, but we're curious about when that function intercepts the 0, which is cool. So essentially now we've created a hybrid of these two functions, and where they intersect will indeed be the 0 of the new function we've created, which is 7x minus tan x. So we do set it equal to 0, but we've kind of invented a new function to solve this intersection. So now that we have our function, we can now use Newton's method. And to know Newton's method, we need to know that function, which we do. We also need to know that function's derivative. And we also need to know what x we're starting at. We already chose the x we're starting at, x1 is 1.5. And so let's go ahead and take the derivative of our new function. That's going to give us 7x derivative of 7x is 7. And the derivative of minus tan x is minus secant squared x. And, most people's calculator doesn't have secant on it, so here's a way to rewrite this that's going to be a little more useful. So we could write f prime of x is equal to 7 minus, we could write it as 7 minus secant of x quantity squared, and then we can rewrite it again as f prime of x equals 7 minus, because secant is 1 over cosine x squared. And everybody's calculator probably has a cosine function on it. So now it's time to plug in our x1 value. So we're looking what is our function when x1 equals 1.5? And we can solve for that by plugging in 1.5 to our original function. So we have 7 times 1.5 minus tangent of x, which is also 1.5. And then we'll solve our f prime of 1.5 by plugging it into our derivative function. 7 minus 1 over cosine 1.5 squared. And here it's really important to turn your calculator to radians because we're working in radians, right? 0 to pi halves. So anyways, let's solve for this one first. 1.5, the tangent of 1.5 is 14.10141995. And I'm saving this many decimals because it wants us to be accurate to 7 decimals, which is quite a task, really. And 7 times 1.5 is 10.5. We subtract off our 14.10141995. And we find that this is equal to negative 3.60141995. And that's roughly equal to that. It's not the true value. So we'll put these little, this roughly equal to sign here. How about cosine 1.5? That's 0.070737202. And we're doing the inverse of that, so 1 over that. That gives us 14.1368329. And then we're going to square it. That gives us 199.8500445. And we're going to subtract that number from 7. And so this is equivalently, it's roughly negative 192.8500445. And the trick here now is to plug it into our formula, right? So we're looking to solve for what x2 is. And to know x2, we have to take x1. So x of n plus 1 is x2 for us right now, and xn is x1. So x2 equals x1 minus f of x1 divided by f prime of x1. And we've solved for all those components so we can plug them in. x1 is 1.5 minus this number, which is minus 3.60141995, and that's f of 1.5. And then we're dividing that by f prime of 1.5, which is negative 192.8500445. And now we'll do our calculation. Alright, so what we end up with here is a positive number. It's a positive number here. We're subtracting a positive number of 0.018674717, and we're subtracting that from 1.5. And that gives us approximately, so x2 is approximately 1.48132523. Now, here's where I'm going to stop doing this process. If you wanted to do this all by hand, well, firstly, you'd be a maniac, because nobody wants to do that much calculating. And secondly, what you would do is you would take x2, and now you would treat x2 as x1. So now this would be, now we would look for x3. And x3 would be equal to x2 minus f of x2 over f prime of x2. And then we would solve for x4 and x5 and x6, and the process would still be the same. Now, this has gotten us closer to the answer than 1.5, but it could take many, many iterations to get this accurate to the 7 decimal places. So once you really know what's going on, and hopefully watch my video on Newton's method, I recommend just using a calculator, because this is computer work. This isn't human work. So I found a nice site. It's Wolfram Alpha Widgets Newton's Method Calculator. So if you look up Newton's Method Approximation Calculator, the second option will be Wolfram Alpha Widget Newton's Method Calculator. And what we can do is we can just plug in our function that we created, That was 7x minus tan x. 7x minus tan x. And we're going to start at 1.5 because that was a pretty good guess. And then we're going to go ahead and hit solve. And it's computing. It even took the computer like 3 seconds. That's a lot of work. And what it spits out is after many iterations, what they found was that x is approximately equal to 1.47419241926197, and I think we're past 7 decimal places. 1, 2, 3, 4, 5, 6, 7. Cool. The 1 rounds off, so we just end up with x is approximately equal to 1.4741926. And let's check and see if the MyMathLab agrees. Okay, MyMathLab says 1.47 41419926. So we're good. We got it accurate to 7 decimal places. We didn't have to do many iterations of Newton's method. And it's also important to know that your guess will make a huge difference in how long this will take. If I had guessed like 0.1, it would take much longer to get closer and closer to my true intersection. So it's important to graph things and kind of know what you're working with before you make a guess. And then, of course, also use your tools. I think this would just take way too much time. So as long as you know how to do the method and you understand why it works, I think at that point it's perfectly reasonable to use this Wolfram Alpha Widgets Newton method calculator, or any other one you may find. Another way to double check your answer, if you have like a TI-82, you can graph both of these functions and you can look at where their intersection is that's slightly less than pi halves, and there is a way on that calculator to find the intercept. And so that's also a good method of getting to the end step without doing the very tedious work of Newton's method multiple times. So I hope this was helpful, and I'll see you next video.